Hi guys, we're doing a video on numbers 6 and 7 on the test review 4. They look very similar, but they have very different approaches, so I think this is a really good comparison to make. I'm going to start with number 7 because I think this one is following the rule that we might think both of them are following. And then once we do this one, we can see why number 6 doesn't use the same rule. So I've copied number 7 down. And to me, this looks a lot like a chain rule because this power here on bottom is 3, on top is 2, which indicates to me that this bottom is probably the inner function g, and the top is g's derivative of some form. Another thing is I can't really break this up at all without using partial fraction decomposition because there's so many terms in the denominator. And then also if you just glance at it and try to do g prime, you should get 6x squared and 4, which is double what we see on top. So I can see that eventually I'm probably going to be multiplying by 2 to try to compensate for that. So this definitely fits the bill for chain rule. Remember, for chain rule, because what we're doing is anti-deriving, our answer should look like this, which is the function f composed with g. But what we see in front of us should be the result of the chain rule, which means we should have g prime somewhere on here, and we should have f prime with g inside of it somewhere on here. And so whether you do inspection or substitution, those are the two parts you're kind of looking for. And you want to identify that g first because it's still inside of composition. So I'm going to do both methods simultaneously just because I don't know who's going to watch this and which method you're using. But for inspection, I would say my g function is the denominator here. And we have to check for g prime. We just said what it was, so if you're not wanting to write down all these notes, you can do this part in your head. Like I said, we just talked through that, and I could see right away that this needed to be multiplied by 2 to get to here. And there's just some evidence. Okay, so we're going to multiply the top by 2 so that it looks more like g prime. And to compensate for that, we also need to multiply by 1/2. And now this part on top is our g prime. And then the 1 from the numerator that's left over and the denominator together would be our f prime. So let me go ahead and write that down so you can see what I'm talking about. Because g was in the denominator, we'd have to make it 1 over g. And so there's our f prime, here's our g prime, there's a coefficient which is allowed to be there. But basically we've confirmed that we have both parts of the chain rule, but our final answer is just antiderivative of f with g inside of it. So that's our last piece, is to figure out what the antiderivative of this is, and that should be our answer along with that coefficient. Okay, so our final answer for inspection method is the 1/2 from the front, and then the antiderivative of f, or I guess f, because I wrote f prime, and then g inside. So if you go back and take the derivative of this, you should see that you get the 1 over g, because that's the derivative of natural log, but then multiplying by g prime, that second part of chain rule, is what will produce this numerator. If we did u substitution method, the u would be, again, the denominator, same thing as g. We take the derivative with respect to x, same step, and here's where we deviate. I still like to factor out the 2 to make it really clear how I'm adding in a 2 to the problem. Another option that you have here is if you don't want to have to multiply and divide at the same time, if that's confusing or something that you think you might forget to do, you can, over here, divide by 2 to create exactly what was already in the problem, and that way you don't have to think about adding in the 2 there. So now this is exactly what was in the question, and this is exactly what was in the question, and so we're going to replace that piece with 1/2 du. So now my integral would be 1/2 du, and then from the u part, it was 1 over that. And so I'm going to pull the coefficient out. Oopsie, don't do what I just did. I wrote the antiderivative, but still have an integral, which is not proper notation. So we took the 1/2 out, we still have the integral. And now finally taking the antiderivative of that, which is kind of the same question we had over here in the inspection method. So we'd have the same exact answer. Natural log u. Okay, so that's great. We've got our two methods. This seemed to work out really well with chain rule. And number 6 looks very similar when you just glance at it. It's also, I don't know why I wrote 6x. It's also a fraction. And one part of that fraction has a higher power than the other. So the same kind of clues that I was saying we should look out for on the last problem. But if you try to attempt it with chain rule, you're going to find that something goes wrong. If we do g as the larger of the two powers so that we can take its derivative, right away I'm getting one problem, but this isn't the only one. One of the problems that I have is that my g prime has two different terms, but what appears to be g prime, or should have been g prime, only has one term. I don't have a way of multiplying in to create a new term without multiplying in an x, which you can't do with chain rule. That would be a whole different method. So there's one problem. Let's try u substitution method. Okay, here's my second problem, even with a different method. If I just ignored this, like let's say you overlooked, okay, you know, maybe it's right, there's an x there, maybe I just need to multiply this by 3 and the 4 will work its way out. The other issue I have is that our derivative is on the bottom of the fraction, but our dx would be considered part of the top because it's not under something. So this wouldn't be able to substitute in place because the expression part of this is on the bottom. It would be 1 over 2x, but I have a polynomial, not a fraction. It's not rational. So I'm not going to be able to substitute without doing other operations that I'm not allowed to do with chain rule. That's, again, a totally different method for antiderivatives if you want to go that way. So how can we do it with the skills that we have? One clue is what I kind of hinted at with this problem, which is that if you wanted to, you could split this fraction into smaller pieces using partial fraction decomp, which is, you know, not, I would say that's definitely not worth your time to do here. That would be a lot more work to do. But here it's a little easier because it's a single term in the denominator. So if you think of this like with numbers, you're allowed to split this apart because operations in algebra should be reversible. So if I'm allowed to take these three fractions with the same denominator and add them together to get this, then I should be able to take this fraction with the three terms in the same denominator and split it apart. It's reversible. So that's what I would do here. If we split this into three parts, all with the same denominator, because that's how they got to this state in the first place. And then you reduce. Now you just have some weird polynomial where each of the terms looks a little different, but they're each individually things that we know how to take the antiderivative of. So I'm going to think of them like separate antiderivatives and keep them together with addition. All right, that's my suggested approach. Oh, and if you're watching this, just one more comment on this guy here. We did this problem in class a couple of times. You can get a variety of answers for the antiderivative of this. If you factor out the 1/2, you'll get this. If you don't factor out the 1/2, then you'll get this. And we were saying that both of those were valid antiderivatives because this 2 acts kind of like part of your constant at the end, which we haven't identified because we don't have a point or any other information to figure out what the plus c part of this is. So this is just a constant, and it just becomes part of the constant that you don't know. And these two problems really are describing the same they're not the same antiderivative, but both functions have the same derivative. In fact, we were showing in class that you could change this constant to any number you wanted. Because of this log property that splits it, the main part of this function with the variable is still the same, and we don't know enough to verify whether the constant's right or not, so it doesn't matter what that number is. And you can test it by taking the derivative of yours along with the one I put on the answer key, and they should give you the exact same thing, which is 1 over 2x. All right, let me know if you have any other questions. Thank you for watching.